All right, this is Mr. Craig, and this is part 2 of the buffer question, and we're going to concentrate on question number 2 here, which says calculate the pH for each, where we have a 0.45 molar potassium benzenate, and then we're going to add a strong acid to that. All right, first thing that I want you to recognize is that we have a salt. We know we have a salt because we have a group 1A metal in front of our common ion. And our common ion in this case is from our benzoic acid. So if we know that we have benzoic acid and a common ion, you need to ask yourself, how will the C7H5O2 behave when it's placed in water? Well, if it's a conjugate of a weak acid, it has to behave as a base. So what we want to do is dissociate the salt, and again, it will dissociate to 100%. And you will see that on the AP exam when we're working with any buffer questions, unless you have a KSP type problem. So once we have our salt dissociated, the only ion that we are concerned about is the benzenate ion. And the benzenate ion is the only ion that is initially in the solution for this type of question. That's one reason why you'll notice that there's no values for the hydroxide or for the conjugate of the benzenate ion, which is the benzoic acid. Now, one thing I want you to recognize or ask yourself is, how does this cause the solution to become more basic? Well, the benzenate ion actually reacts with water, and it will rip a hydrogen off of the water and place it on the benzenate ion to make benzoic acid. Also, as a result of the ripping off of the hydrogen from the water, you're going to be left with OH, or hydroxide ions. And anytime that we have hydroxide ions present in a solution, we would expect the pH to be above 7, or a basic solution. So as stated previously here, we're going to start off with no hydroxide or no benzoic acid. We're going to have our positive X's over here, our negative X's over here, but again, doesn't matter because we're using the 5% rule. So since we have hydroxide in our ice chart, we need to find a Kb value. So anytime we have hydroxide in the problem, we need to have an expression that has hydroxide within it. So we'll rearrange the variables from our expression in this step right here, which you can find on your equation sheet. Make sure you can find that. To solve for our Kb value, so we'll plug in our Ka. We know that the constant is a constant, so find out what that value is for the Kb. And then we can solve appropriately for the hydroxide concentration. So we'll plug in, or actually write our expression first, plug in our respective variables there. So I have x's for each, because again, at equilibrium, or the equilibrium step, we have x. Again, you'll notice that there's the negative x in this step here, but we lose the negative x over on the next step because we want to use the 5% rule. So once we've got to this step here, let's go ahead and rearrange variables so that we can solve for x squared. And once we have x squared's value, we need to find out what x is equal to so that we can find out what the hydroxide concentration is. Once you have the hydroxide concentration, then it becomes very simple. We can find the pOH first, and then we can solve for the pH. So the pH for this salt is 8.92. Now again, remember, that's a real quick check to make sure if you're doing things correctly. If you're adding a salt that is a conjugate of a weak acid, it better behave as a base. So in this case here, we do have a solution that is on the basic side of the scale, which is a good thing for us. All right, in part B, we're now adding a strong acid, and we're going to add the same amount that we did in part A, but again, this is a brand new beaker, brand new situation. So again, we're going to set up our ice chart, but what I want you to notice is the difference between this ice chart and the ice chart up above. I have hydroxide in this ice chart where I have hydrogen in this ice chart. The reason for that is because we're adding a strong acid. Since I am adding hydrogen ions, I want to have hydrogen in my ice chart. And again, ice charts are for organizational purposes here. But one thing that I want you to notice is that we have our concentrations for our benzenate ion and our hydrogen ions, and the benzenate or benzoic acid is approximately 0. Now we're not going to do the actual concentration here. I'm going to stick with the 5% rule for the sake of time so we can go through this quickly. And I would expect you to do that on the AP exam as well. Now, whichever of these two concentrations is smaller will go to 0, and in this case here the hydrogen goes to 0. It goes to exactly 0. And what's going to happen is, since this is an equilibrium problem, it'll get something back from the weak acid here. So that's actually what we're going to solve for when we solve for the pH, because there's no such thing as a solution with absolutely no hydrogen in it, at least with what we're dealing with. So again, we're going to use our Ka expression because we have hydrogen in the problem. Set up your expression, rearrange the variables here. You may plug in the values there, which would be highly recommended. And you'll notice that we only have to solve for the hydrogen concentration in this step. So we don't have an x squared. There will be no square roots. But what I do want you to notice is that the pH is 4.93. Think for a moment. What was the pH of the salt alone? We'll answer that here in a moment. Now, some of you are very, very comfortable with working out the equilibrium steps like this, but in this case here, we have concentrations of the weak acid and its common ion. If you have that scenario, you may use the Henderson-Hasselbalch equation. Some of you don't like to use it. That's fine. I think it might save you a few seconds, maybe in some cases a minute or two, when working out the problems. But if you do not understand what's going on with the Henderson-Hasselbalch equation, don't start trying to figure out on the AP exam. Continue with what's comfortable here. However, if you do know how to use it, I highly recommend it because it is a quick process to help you find the pH and the same answer. You'll notice that the answers for the pH for both of these are the same. But let me explain what the Henderson-Hasselbalch equation is. Again, you have your pKa, and again, anytime you have a p in front of anything, it represents negative log. So the negative log of the Ka value, which I have shown here in this step here, and then we're going to take plus the log of the anion from our acid, hopefully weak acid, and then we'll plug in our concentration of our weak acid. Now these values aren't so clear all the time. So sometimes what we have to do is we have to come up and find out, okay, which of these two is more negative? Well, the benzenate ion is actually more negative than the benzoic acid. So this concentration, the benzenate ion, will act as our A-. And you'll notice that that is the anion. It is the negatively charged particle. But most of the time, it is negative, but sometimes it is positive, but it still is more negative than the weak acid. I don't even want to get into that discussion at the moment. All right, so we can plug in our concentrations, and again, I would highly recommend that if you're typing it in on your calculator, that you type it in as you see it here. That'll keep you out of trouble from doing something weird, even though the calculator should recognize how to register a log value there. All right, so our pH is 4.93 after we add the strong acid. Coming back down, one thing I want you to recognize here, in part A, our pH was 8.92, and in part B, our pH was 4.93. That's a big change. That's a pretty big change. That's almost 4 pH points. So even though the solution was very capable of absorbing the hydrogen ion concentration, it is not a good buffer. The reason why it's not a good buffer, again, make sure you know what the definition of what a good buffer is. It has the capability of resisting a large change in pH. And even though it did absorb the hydrogen, the pH went from a very basic solution to a very acidic solution. So we would not use this or consider this as being a good buffer solution. Take a look at part C to see an example of a good buffer solution, hopefully.